When protecting high-value assets, the instinct is to build a thicker wall, a heavier door, and a lock that cannot be picked. We want physical certainty that what we secure stays exactly where we left it. Digital inheritance platforms and password managers try to replicate this certainty. They promise to hold your encrypted vault and, upon your death or a prolonged absence, pass the keys to a designated beneficiary. But look closely at how this architecture is built. A client passes wrapped keys and ciphertext to a server, and access is governed by database permissions. A single central node determines who gets the keys and when. That central node represents a single point of failure. If an attacker breaches the platform, if an insider is coerced, or if the custodian simply goes bankrupt, the rules of access can be altered or erased entirely. Heritage approaches this differently. We replace the custodial database trigger with a system of strict cryptographic enforcement, ensuring that no intermediary holds the power to block or bypass the inheritance logic. The architecture relies on three distinct layers: a zero-knowledge encryption stack, an active liveness state machine, and a decentralized time lock protocol. By eliminating the central control point, the responsibility for data release moves away from the custodian's discretion and into the execution of the cryptographic protocol itself. The foundation of this system begins with a strict isolation constraint. The backend, built on Rust and Postgres on isolated infrastructure, is configured to receive and store only ciphertext. It has no capacity to process raw data. This block diagram illustrates the boundary between the local client and the backend server. All vault contents are encrypted on the user's device before transmission, utilizing authenticated encryption, AES 256 GCM, and XChaCha20 Poly 1305. To maintain a pure zero-knowledge state, the architecture uses a two-layer key scheme. First, per-asset data keys are generated locally for every discrete piece of data in the vault. Second, those individual data keys are wrapped under a master user-derived key. This creates a distinct separation between the key material and the ciphertext itself. This strict separation ensures that plain text keys never cross the network boundary. Only the encrypted data blocks move to the server, while all key layers stay firmly on the local device. Authentication runs through a dedicated identity layer that holds no vault data. Access requires physical liveness checks and document capture verified by HMAC webhooks. Sessions are strictly device-bound, utilizing single-use hash-stored links rather than bearer tokens. Because keys and ciphertext never intersect on our servers, Heritage is mathematically blinded to the contents of the user's vault. We hold the locked boxes, but the mechanism to open them does not exist on our infrastructure. For a vault to be both secure and retrievable, the architecture must account for the passage of time. This introduces the concept of continuous liveness. Most digital inheritance tools use a passive deadman switch, a database query waiting for an expiration date. Heritage uses an active client-driven state machine. This flowchart outlines the progression. While the user is active, the system remains in the first state. If a check-in is missed, it moves sequentially into a missed heartbeat state, triggering direct owner escalations to confirm their status. If there is no response, the machine advances through pre-alert, into a countdown phase, a delivery grace period, and ultimately to the release state. At any point before release, the owner can trigger an override to reset the cycle back to active. The user configures the pacing of this sequence. They set a heartbeat interval, ranging from 15 to 90 days, which dictates how much time must pass before the system transitions to the next node. Every time the user successfully logs a heartbeat, the client application executes a local key rotation for the entire vault. The assets are fully re-encrypted on the user's device, replacing the old lock with an entirely new mathematical structure. This continuous cycle provides post-compromise security. If an adversary manages to extract a key, their access is limited by a strict expiration date. At the very next heartbeat, the old key is cryptographically retired, rendering the leaked material useless. This creates a specific technical hurdle. If the backend is blind and the keys never leave the client, there is no obvious way for the platform to deliver a usable package to a beneficiary once the owner is no longer active. The solution operates outside of the Heritage platform, utilizing a protocol called time lock encryption, or TLOC. Looking at this timeline, the data packet isn't targeted at a specific user's public key. Instead, TLOC leverages the League of Entropy's DRAND network, a distributed randomness beacon, to aim the encrypted material at a specific timestamp in the future. Instead of locking the data with a static key belonging to the beneficiary, the client application encrypts the release material to a fixed point in time. That future point correlates directly to a specific sequential numeric round broadcast by the DRAND network cluster. This creates a rigid mathematical constraint. The release material is securely encrypted, and the decryption key literally does not exist until the network reaches that precise round. Heritage's only role in this phase is to route this time-locked package to the beneficiary. The platform never interacts with the contents of the delivery. By offloading the unlock mechanism to an external, decentralized beacon, the release process is completely decoupled. Heritage cannot force an early release, and the assets remain accessible even if the company itself disappears. The final step is executing the decryption once the DRAND network reaches the target round. This requires a mechanism known as threshold BLS signatures. As shown here, the DRAND network consists of independent nodes, each generating distinct cryptographic fragments. Security is distributed across the cluster. No single node holds the complete private key to decrypt the package. For each successive round, nodes independently generate partial signature fragments. When a specific percentage combine, they form the complete key that unlocks the data. This is the threshold constraint. The final signature is only valid when a mathematical minimum of these independent partial signatures are aggregated. Because the signature requires this distributed threshold, it is impossible to predict or accelerate. No single entity, not a rogue node, and certainly not Heritage, can force the network to produce that signature early. Once the target round hits, the aggregated signature is published by the network. This immediately and deterministically unlocks the time-locked release material for the beneficiary. The entire pipeline flows without centralized permission. Client-side authenticated encryption secures the payload, the active heartbeat rotates keys locally, and decentralized BLS signatures execute release. The defensibility of the system is the architecture itself. By decoupling storage from cryptographic enforcement, Heritage delivers guaranteed digital inheritance while structurally eliminating the possibility of custodian interference.